Derivation of the discrete time convolution sum. In learning outcome 1.4, we gave an example of using LTI properties to determine the output of a system. If we know that a certain input produces a certain output, we can apply the scalability part of the linearity property. If we know that another input is a scaled version of that first input, then the output will be a scaled version of that first output. The same idea can be extended to the additivity property of linearity, as well as to time variance, which says if we shift our input, we will shift our output. So therefore, if our x is the scaled version of x naught plus a different scaled version of a shifted version of our input, the output will be a sum of scaled versions of this first output. Let's consider a special input, the unit impulse function. This is special because any signal x of n can be built from those impulse functions. No matter what we want to make this in discrete time, we can choose scaling values and shifting values to produce this from this function. Therefore, our output will always be a sum of scaled and time-shifted versions of the output here. If our input is a unit impulse, we say that the output of our system is a system response. Therefore, if the input is an impulse, the response will be an impulse response. This is a special terminology. We're going to use it throughout the course. That impulse response is denoted by the letter H. You need to memorize this, write it down on your note sheet. We will use H and impulse response interchangeably. Therefore, if x can be built from any combination of scaled and time-shifted unit impulses, our output can be produced from any combination of scaled and shifted impulse responses. Let's take a look at this equation a little bit more closely. This 2 comes because our input function had a value of 2 at time 0. This h is scaled by 1, and that's because our input had an amplitude of 1 at time 1, and that time 1 is this amount of shift here. We can then rewrite this equation that 2 is our input at time 0. There's a 1 here, which is our input at time 1. Our input function really had values from minus infinity to plus infinity. So at time -1, it had an amplitude of 0. So what you don't see written here is that it's also x of -1, which is 0, times a shifted version of that output shifted to the left by 1. And you don't see that our input function x had an amplitude of 0 at time 2, so this output y was also a scaled version of that h. Because this x2 and this x -1 are both 0, it doesn't affect things. If we had a different function x, which had non-zero values here, we would then be adding more terms. And we would be adding those terms for as many terms as there are x. This time argument for x, we can consider the variable k. So we're going to produce our y of n by adding up these x's times these h's for k starting at -infinity, going positive until we reach positive infinity. That k value is also the amount of shift in our h. We can generalize this in this convolution sum, where we're adding over k values, going from minus infinity to plus infinity, of h's shifted by an amount k. This is our convolution sum. It has an equivalent in continuous time called the convolution integral. Its derivation is a little bit more tricky, so we're not going to go into it here. But you should be aware that it exists, and we will also use this. We will go into the practical issues of how to use this convolution sum in learning outcome 2.1. And we'll go into the practical issues of how to use this convolution integral in learning outcome 2-2.